I only did number 5.
Do number 1 try.
Okay. All right. So you guys ready? Here we go. Number 1 was here, and you had this reaction. It was carried out. It only contained the reactant, so that's where I got this value for just the reactant. I don't know if I can make this just a scotch bigger without losing everything. Yeah, I can. Okay. So that was my reactant. I didn't start with any product at all. Okay. And then I know that I'm going to be taking away from the reactant because I don't have any product to take away from. So I've got to be subtracting this. And I'm subtracting x from here. And I'm adding 2x. It has to be 2x because there's a 2 coefficient here. That means in the end that I'm going to have 0.055 minus x over here and 2x over here at equilibrium. Everybody okay with my ice table?
Yes.
All right. I got the 0.36 that's here. My reactant value then goes on the bottom. My top value then is this, but I have to square it. So that's going to be 4x squared here equals this guy. So if I flip all of this stuff over here, I can put that into the quadratic if I'd like. I did find my cable, so I can give you guys the quadratic formula, or I can, we can go over here and use this guy, quadratic formula calculator, because they're never going to give you one on the exam, so you would always have access anytime that you need to do this. Okay, yeah, I want you skinny though. There we go. Okay, so my quadratic formula here for A would end up being 4. My B would be a 0.36, and this would be a negative 0.0198. And I'm going to calculate that now. So here are my answers. Okay, come on. Stop being a brat. There we go. So when I get over to here with my quadratic formula calculator, this is the only valid one because, of course, it's not going to be a negative value. So this is the same as this, right? So then if I plug that in, I would take this minus this to get my answer for this guy. And then I would take that value and multiply it by 2 to get my answer for this one. Does that make sense?
Yes.
Yeah, because it's 2x. This is x. This is 2x. Hens. Does that make sense? Okay. All right. Any other questions on number 1? All right.
I'm more concerned. What's the answer for number 3?
I thought I took number 3 off, didn't I?
It's a different problem.
Yeah, it's not even
Oh, okay. All right.
I don't think
Is this your 3?
No. You want me to read it to you?
Yes.
Just bring me your pen.
At a certain temperature.
When you would do like stoichiometry, or when you would use the axis, but no, we can use it when you have the kick value, you can use the axis.
Why did you only do number 5?
Is this it right here? So exercise 9.
Yeah.
So if I go back over to my keys and I find exercise 9 up here. It's right here.
Oh no, there's a big sticky note on it.
Yeah, there is. I But here's your answers.
Oh my gosh, I didn't even do it right. I did the wrong, I solved the wrong thing. I'm so disappointed. Or did I go wrong? Those things we done.
Oh, you needed 3 answers?
There's 4.
4 answers? Oh, yeah.
Yeah, I got 1.
Remember 3? Yeah, you did 1.
I have 1.
It was right, though. No, it wasn't.
I think.
We did, but Lowe's was already here. At the power
And then you do that, and then you put it.
Yeah, so then you
Talk
got
about
it.
not I'm not even on the basketball team. Me? Until you're on a home state? You love it.
I don't know. I just put it out there.
All right, so this is the one right here. Okay, I can do it right on here then. Comment. So this is my PCl5, PCl3 plus Cl2. Okay, everybody cool with that? Just copying the equation down.
Yep.
All right, certain temperature, the flask initially contained the PCl3, which is 0.298, and 0.0087. No, that's the wrong place. Hold on. Back the train up,
Where
Lippy.
did you even get that? That's
Right here.
the thing. But how do you know it's 0.00?
It's the 8.7 times 10.
So you take your decimal and move it 3 spots this way. 1, 2, 3. Fill in the loops. Okay. So when we got done, we had 0.002 here in the flask, right?
Yeah.
And we started with 0. Yep. Okay. So we had to form 0.002 of that, which means that we formed is this balanced? Yeah. 0.002 of this. So that's going to take us up to 0.3 here. And then we would have used up 0.002 here. So that takes us down to 0.0067. Yep. All right. Cool. All right. So then K is going to end up being, we're going to take 0.3 times 0.002 over 0.0067.
I did that right, except I just had 0.296.
Okay, I heard some whats. What's going on? What's wrong? So that ends up being that value down there. Questions?
Oh, I did have all the values. I just didn't have them like that. Oh, I did too.
Except the K value.
Okay. All right. Let's go back over here.
I have a question.
Yes.
When do you use the X's and when do you just like use the numbers?
Well, if they don't tell you, you have to use an X, but they gave us the numbers. So you have to read through it and see what they've given you and what they're asking for. They're asking for K here, so we're not going to be solving for these values. They'll have had to have given us the information to get there.
So when it does give us a K value, we use X.
A lot of times, yeah. All right. What's your next question? Is it this guy? Does this look right? Okay. So this is one that you would have had to use the quadratic equation for, because they didn't give us a way to solve for it otherwise. So you've seen all of my math going through here, figuring that out. They gave us 3 different Kc values, so we had to come up with 3 different answers. Okay. So there's varied, and we ended up having different, but you had to use the quadratic equation every time to do it. So.
Oh, I see.
All right, questions on number 5. I assume your number 5 was the same.
Yeah, my number 5 was good.
Okay.
I did it right.
I was smart.
Now I have no idea what I was
Did
doing.
you have a number 6?
Yes, we had number 6.
Okay.
Not that.
Did your number 6 look like this?
Yes, it did.
Okay. Let's see if I covered that up with a Post-it note. There's your number 6. Is that right? Carbon monoxide?
Yeah.
Is that the same one? Okay. So again, yeah, this one was kind of nice because you could do the square root of both sides for this, and then you could end up getting the answer for that. So that's an example of something like you would see on the AP exam where you could get out of it without having to use the quadratic. All right, was that it for your homework last week? Done? 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 How much? Done. Half? Done? 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 Evie? Done?
I'm done.
Okay. All right, hon. Watch the video, okay, hon?
You didn't look at what I said on the board. I did.
All right. You guys ready to go?
E.
All right. I'm going to come back to 7-8 after 7-9 and talk about that. So we need to talk about some stuff in 7-9 to get you to 7-8. So this is the Le Chatelier's principle. Sometimes we call it Le Chat. Okay. And he said that a system is going to act at equilibrium until a stress is applied. So stress can be applied in a variety of different ways. It could be applied by increasing the pressure. It could be applied by adding in or taking away some of your products or reactants. It could also be affected by a change in temperature. Remember that temperature is the only thing that K can be changed by. So the only thing that's going to change K is temperature. So any questions about any of that? All right. In an endothermic reaction, an increase in temperature is going to end up giving an increase in K. Exothermic, it's going to decrease K. So keep that in mind. That might be something that you want to highlight. Le Chatelier's principle is useful in determining how a reaction at equilibrium will react when we apply a certain stress to it. For example, if some of A is added, then the concentration of A is increased. That's going to disturb our equilibrium. So if we add in A, if we're pumping more of this in, that's going to cause the reaction to shift and form more products. Because you're adding more of this stuff in, it's going to shift it that direction to use up some of that reactant to get it back into equilibrium. Does that make sense? If we pulled some of A away, then it would have to shift the other direction and make more A. So if we pulled that A out, it's going to shift it the other direction to make more of it. Because the Kc value has to remain the same. If the concentration of a product is increased, then the reverse happens. So if we increase D, it's going to shift and form more A. Or if we take some of D away, it's going to have to shift to form more D. Removing reactant and product is going to decrease it or increase it. If we consider a gas phase, then the equilibrium expression is written like this. When you're working with a system that involves gases, the change in pressure can cause that to shift the reaction. If the pressure is increased, okay, so if we increase the pressure, then it will alleviate that stress by reducing or shifting to the side with fewer moles of gas. Increasing the volume can also impact that, because if we increase the volume, we're going to decrease the pressure, and that's going to change it. So if we're looking at gaseous reactions, so here, which side has more moles of gas? This side or this side? The first side, okay? So if we increase the pressure, it's going to shift it over here to reduce the moles of gas. If we decrease the pressure, then it would shift it this direction. The final stress on a system is for temperature. In this exothermic reaction, we're going to think of that delta H is negative, okay? So we think of heat as a product. So if we cool, what are they going to do here? So if we cool the system down, it's going to shove it this direction to make more heat. So if we pull some of that heat away, it's going to shift it this direction. If we add more heat in, then it's going to shift to this direction to create more, okay, to pull heat out and store it in bonds. Catalysts do not affect the energies here. They don't affect the equilibrium, so keep that in mind as well. Okay, so Le Chatelier allows us to predict the effect of what stresses will have on different systems. And we're going to look at that. That's our lab in this unit, is looking at that, is the Le Chatelier lab that I handed out yesterday in class. So we'll start in on that on Thursday. All right, so let's look at this guy. We've got an endothermic reaction. This is going to decompose into carbon monoxide and chlorine gas. The KEQ for this is 0.0071. Using Le Chatelier, predict how the reaction will respond to each of these stresses. If we add more of this in, so we're adding more of this in, so we're adding it in, that's going to shift it to, and they want you to know, they want you to call it left and right. Okay, so they're going to shift this to the left, or to the right, I mean, shifts right. This is going to shift to the right. The reason why they don't like you to say reactants and products is because these are the reactants for these products, and these are the reactants for these products. So they like you to say shifts left or right. Does that make sense? Okay. So if I pull some of this away, I'm pulling this out of the system, it's going to shift to the right because it's going to need to form more of this stuff. All right. If I increase the pressure, how many moles of gas do I have over here?
1.
How many do I have over here?
1 and 1.
Which is
2.
2. So if I increase the pressure, which way is it going to shift?
To the left.
Shifts to the left. All right. Now,
Is it just because if there's more moles on one side?
yep. So if we have, this is 1 mole here, right? This is 2 moles because 1 plus 1 is 2. Yes?
Yes.
All right. So if I increase the pressure, it's going to want to make fewer moles of gas, which will then decrease the pressure. Because if you have fewer moles, you're going to decrease the pressure.
I see.
You get it?
So when it takes some of this stuff and makes it into this, we've reduced the number of moles in there. And that's going to decrease the pressure some. Okay, everybody cool with all of that stuff before we get into temperature?
Yes.
All right, they said that this is an endothermic reaction. So we're going to consider heat to be on this side, the left side, or is heat going to be on the right side?
Heat is going to be on the right side. No, left. Yeah, no, it's on the left.
It's over here. Okay, so it's endothermic. It's going to be on this side of the reaction. Okay, so if we decrease heat temperature, we're pulling heat away. We're taking that out.
So it shifts to the left.
So it's going to shift to the left to make more heat on this side. Yeah.
Because there's more heat.
Well, it wants to make heat. We're pulling heat out. They said that we're decreasing the temperature, right? So if we're decreasing the temperature, we're pulling heat away. We need to make more heat to compensate for that. You're taking it out of there, so you got to make more now. Well, it'll probably go down a little bit, but it'll maintain. Just like yesterday, we looked at these. Oh shoot, wrong. I forgot that it doesn't go that way. You remember when we did this, you know, it goes up initially, so we pull out the heat, and then eventually it's going to change, but it'll settle down. Okay, it won't be at the exact same spot anymore. That'll change it. All right, Haber process. If you want to like do some interesting historical kind of reading, scientific anyway, this Haber process is actually fascinating. This is one of the processes that has allowed the world population to get as large as it is. Prior to this Haber process, there was a lot more famine and stuff around the world than there is now, because what this allowed us to do was create fertilizers where we had very little in the past. So this ends up being used as a fertilizer. And they will commonly have this, they'll say anhydrous ammonia, like out in farmers' fields in the spring, you'll see big tanks of it. And they're using that as fertilizer out in those fields, okay? So the guy that developed this, he also went on to do some kind of icky stuff, but this is the best thing that he's known for. So, but kind of an interesting historical figure scientifically. All right. So it's determined that increase in the temperature causes the equilibrium to shift toward your products. Okay. Does that mean that it's endothermic or exothermic?
I said endo.
No, it is endo.
Okay. Well, let's go back up here and read our thing. I thought I had that written down. Yeah, here it is. The value of K is, yeah, here we go. If it's exothermic, an increase in temp will decrease the K. If it's endothermic, an increase in temp increases the K. So our K increased, it has to be endothermic then.
Yes!
Okay. So why is that? Well, if heat is over here and we increase the heat, so we're adding in heat, right? We add in heat, that's going to cause it to shift this direction, yes?
Yes.
That will then cause this number to go up and this number to go down, which will increase your K value. Does that make sense? Kind of algebraically, does that make sense?
More heat in the reactant is more product.
Right. So because, ladies, so if you increase the heat, if it's an endothermic process, okay, then it's going to force it over to the product side because it's trying to get rid of some of that heat by going over to here. So an increase in heat is going to cause it to shift this direction. If we increase the heat, if we increase the amount of product, then that top value goes up, the bottom value, your reactants, goes down, which will lead to an increase in K. Make sense? Okay. If the reaction is at equilibrium and the pressure is increased, which way will it shift?
Right.
Left. No.
Which side has more moles?
Right side.
So this has 4 moles, this has 2 moles.
Yeah.
Okay. If we increase pressure, which way is it going to go?
Right.
Right.
It's going to go this direction. Okay? Just to the right. Does that make sense?
Yes, it does.
Because you're trying to reduce the number of moles of gas that you have.
LPF. Is inter LPF or is that intra? Intra is LPF, right? So inter is
No,
bond.
enter is LDF.
Oh, yeah. Intra
Intra's
is
like on the
bonds.
in, yeah. Intra is like, and then
Interstates.
intra is, inter is between.
Inter is LDF. It's like that's
Between molecules, yeah, and then intra is within the.
So as
So we
our
are doing
temp
LDF.
is reduced here, because they're talking about taking our temperature down here, right? So what they're saying is that in order to create the largest amount of product possible, they're going to allow the reaction, they allow it to come to equilibrium, then they cool it really fast. Okay? So how does that work? Well, as the temperature decreases, the molecules are going to condense. And they're going to do that by reforming IMFs, intermolecular forces, okay, in the ammonia. And ammonia has all 3. They have LDF, they have dipole-dipole, and they have hydrogen bonding.
I read that.
Okay? So if we do that, if this turns into a liquid, it is excluded from the equilibrium constant, the Kc value. Kp, is it gases? Kp, I guess it would be Kp. My apologies. Kp value. Okay? So that is going to cause it to shift.
I'm interested in this one.
I'll send a picture of you and say
To the right. forming more NH3. So essentially, guys, essentially, if we have this as a liquid, a pure liquid, that means that we're not going to have any products here. So then we will have this would be a 1 over all of your reactants, and it's going to shift this direction to form more product. And then as that's condensed down, you just keep reforming it until you run out of these gases. Does that make sense? Do you need me to go through that again?
I think I get it.
So when temperature goes down.
Rapidly. Yep. So they rapidly cooled the thing. Okay. When they rapidly cooled it, then this became a liquid. Okay. Well, liquids are not going to show up in your Kp value. So you're just going to have the pressure of the N2 and the pressure of the H3, or H2, I'm sorry, raised to the third power, okay, over 1. So they need, it wants to, because it appears to the reaction, and I'm personifying this, of course, it appears to the reaction that none of this is even present, okay? So it's going to keep running the reaction to try to form more of this. And then as they keep cooling it, this condenses into liquid. And then it's going to keep trying to form and form and form. Kind of cool, huh?
Yes.
I'll shift it to the right. Yep, which forms more product, which is, this is what they use for ammonia on the fields. Until they run out of this. But this is in the air. I mean, 70-some% of our air is this. So for them to be able to figure this out, like I said, this revolutionized agriculture. When they were able to create this and use this as a fertilizer, they could produce more and more and more crops, which then allowed the population to grow. So this was a fundamental shift, a huge discovery that they made, which has allowed our population in the late 1800s, early 1900s to just boom. I mean, if you look at the population growth during that time period, it's like exponential. It's crazy. Okay. Do you have more? I think you've got more notes coming up, right? Is it?
Yeah, we have 7.8.
Yeah, I need to go back to 7.8, but did I include some other stuff in here for us to go through?
No.
Oh, that's the solubility stuff. Okay. All right. Well, maybe I'm not thinking right. Maybe I need to down.
Everyone work that out.
All right. What was I at? Oh, I need to go back to 7.8 then. Okay. So over here on 7.8, where we were talking about this yesterday, you were asking me, well, how do we know if we had to draw this in? How would we know that that was going to work out that way? And I said, well, let me explain Le Chatelier to you tomorrow, and we'll come back to that. Okay. So here we are. So here we ended up calculating these yesterday, and I'll just pull that out from my notes so I don't have to recount. So this was 6. Okay, and then this was 5, 3, and 8. All right. So how do we know? How do we know that, guys? How do we know that if I'm about ready to throw something at you? Stop. Okay. I'm gonna reduce the volume, which ends up doing what to the pressure?
Increases it.
Increases the pressure. So if I increase the pressure, then I've got 4 moles over here. I've got 2 moles over here. It's going to shift this
Right.
direction. Okay, is that what happened? Yes. That's what they've drawn here. Okay,
It makes a lot more sense that we're doing this now.
right. Yep. That's why I said we needed to talk about this today. We needed to just hold on to this idea, and that it makes more sense now, doesn't it?
A lot more.
All right. So here we've got our reaction.
So like, I still don't understand how do you know how many numbers or like how many molecules to draw?
Well, you would need to draw, you would need to take this and show that these are being reduced and this is being increased. And as long as you've shown that that there's more of these and fewer of these, and it's in the correct ratios, then you're fine.
There isn't like a specific number that we're trying to.
Not this time, because they didn't give you a K value. If they would have given you a K value, you might have been able to work that out. But you just need to show at this point that this guy is getting reduced, this guy is getting reduced. And you know, if you reduce this, you've got to make the same amount as what you've reduced this by. So if you took one of these away, you had 1 nitrogen. Well, that means that you could make 2 of these out of that. Okay. But then in order to do that, you would need to have 3 of these, right?
Yes.
3 times 2 is 6.
Yeah.
Okay. So I needed 6 hydrogens to make 2 of these. So as long as you reduce it by the same amount, you've got the same number of circles, they're just rearranged the right way, then you're fine. Okay. But like I said, unless they give you more information, you just need to show that it was reduced. The reactants reduced, the products increased, and then you conserve mass. You haven't created or destroyed any of that matter in the process. But yeah, there's no, like you could have probably, I mean, you could have gone through and created 10 of these, you know, and then you would have had, well, I don't know that you could have, because would you, yeah, then you would have used up all of your H2 in that process. So I don't, and you wouldn't want to use it all up. You need to have some there. So this is probably the only outcome that you could have with what was given. Okay, makes sense?
Yeah.
Okay. All right, so then let's look at this next guy down here, now that we can make a little more sense of this. So this is in a 2-liter container. So, yep, this was the 2-liter was up here. And then they reduced it to 1. So they are just doing the same problem, but now they're having you graph it, okay? So they reduced the pressure, so they didn't add any of this stuff in or take any of this stuff away. So it's still going to be these gradual sloped curves. It's not like this guy where they added him in and he just jumped really fast. Okay, it's going to be still kind of a gradual slope here. So for this guy, these all started out at 6s. So he's going to kind of go up gently, and then he's going to increase. The rest of these are going to go up and then come, is that right? Why would that not be underneath? We're going to have less of that. Starting to question myself. Sorry, you guys. This is the we do, though.
Okay, the messenger. This sounds bad. I don't know. Could have just erased the gun.
I don't feel that strong anymore.
Hate it when they don't hyperlink these things.
I am asking. Sarah said I'm interested, and I said I thought it was a anything.
No. Please.
That's what.
Lovely. There it is.
No, this is me.
Oh.
Yeah, they have it increased. I don't understand that.
The bubbles come out.
I'm gonna have to come back to this one.
Is this how Elton?
Okay, so tonight, you guys can finish up 7-8. You can work on 7-9, and then tomorrow we're gonna talk, I think I have tomorrow scheduled for LaChatelier again, right? Somebody's gonna help me with their book.
Oh, tomorrow is and Q.
Okay, so 7-10 tomorrow. Okay, all right. So tomorrow we'll cover 7-10 and go over that. All right, so that gives you 7-8, 7-9 tonight. Go, go, go. What? I don't know. That's why I need to like, I don't understand. So that's why I said I gotta hold off on this. On this one, I've got to think about that one. So that's why I'm gonna hold off till tomorrow.
We put a filter on it. I do black and white.
Yeah. And then put
All
like.
right, over here.
Like